Now that we are all experts with analyzing electric fields, we're going to move on to a different quantity that's also very important for electrostatics, known as the electric potential. We'll start out again by drawing analogies to the gravitational situation. We've already looked at how similar the gravitational force is to the electric force as long as you swap Q's for masses and electric fields for gravitational fields. You get very similar types of situations. And since the forces follow similar rules, we would expect that there would also be a potential energy associated with the electric energy, just like there's a potential energy associated with gravitational energy. And you might guess the formula, mgy becomes QED. Again, this is only good for constant gravitational fields and constant electric fields, but a lot of times that's what we're going to be dealing with. Now we're going to look at another quantity that doesn't really have a direct usage in gravitational fields. Not that it couldn't, it just tends to not be quite as useful, so we don't do it. We define what we call the potential, which is the potential energy per unit charge when you're looking at the electric case. We could define the gravitational energy per unit mass and get a similar quantity. We don't have a name for this quantity, so question mark here. But if we just look at rearranging this equation up here, this is equal to the quantity g times y. So it's sort of equal to the height that you're at, but you also have to take into account the gravitational field. Now over here we do have a name for it. We call it the electric potential. The symbol we use is a V. The reason we use a V is because this is also known as the voltage, and it's measured in volts, which is kind of silly. It's kind of saying that we have a distance measured in distances, but anyway, electric potential is voltage. I'm sure you've heard of voltage before. It's defined like so, and again, this is only valid if you have a constant electric field. If it's not a constant electric field, you guessed it, you have to integrate something like this to get the voltage in a changing electric field situation. So just to discuss this idea a little bit further. Just like with gravitational potential energy, we can define any location we want to be zero. We can do the same thing with electric potential, as well as electric potential energy. So we're typically not interested in a single voltage because it can be an arbitrary number. The only thing that really has physical meaning is the difference in voltage between two locations. So for instance, if we have some charged plates here, the positive and negative charged plates, we would be interested in the difference in the potential between one plate and the other. And we typically write that VBA means the difference in the voltage between those two locations, B and A, as is shown here. And if we substitute potential energy per unit charge for each of these voltages, we can get an expression like this to indicate the difference in the voltage. And going on, we can combine these all over 1Q. And change in potential energy, this is our delta U, right? That is equal to the negative of the work done. Well, work is force times distance, so we have force times distance over Q. And force is QE, so we have QEd over Q. And the Q's go away, negative signs on both of these. And you can get negative ED will tell you your change in potential energy. I guess I should have Q there so we don't get mixed up. So there's different ways to find your change in potential energy. This is often the easiest way if you have a constant electric field. So we typically take the positive side of parallel plates, or just positive charges, positive electric fields, to be high potential, and the negative side to be low potential. And so if we have a positive particle here, I guess my white pen doesn't work so well on this. If we've got a positive charge here, as it moves from high potential to low potential, it's going to have a change in potential energy. It's going to accelerate going this way, so it has to lose some potential energy as it gains kinetic energy. Now things get a little bit weird because we have negative charges as well, so we don't have a negative mass analog for gravitational forces. We don't have things flying up. So in this case, we still define this side as high potential because this is like characteristic of the field, of the arrangement of the charges, not of the charges in it, of the test charge. So we still call the positive side high potential and the negative side low potential, but now that we're at low potential with a negative, this is high potential energy. We know that because if we release this, it's going to go flying this way and it's going to gain kinetic energy. So regardless of what particle there is, the positive side is high, the negative side is a low potential. But the potential energy, we define that as, I gotta switch colors again. Maybe this was a bad idea. Anyway, we defined U as QED. So that has a charge in it, and the sign on that charge determines your potential energy, and thus your changes in potential energies. So it gets a little strange that way. Let's go ahead and look at another analogy. So we could think of a given height in a given gravitational field as the gravitational potential here, where it would be the charge, or sorry, the energy per unit mass. Oh man, I gotta switch back again. Sorry about this. So energy per unit mass over here would be the same for anything, whether it's a big boulder or a small boulder. This one would have more energy total, but the energy per unit mass would be the same at that level. So that's what this potential idea is getting at. The potential here at B is going to be the same regardless of the amount of charge, just like the energy per unit mass here was the same. Energy per unit charge here is the same. Now this is going to have more total energy, just like this has more total energy because of the size there. Alright, let's look at some common voltages. These are potential differences. So often we don't call them voltage differences, even though they are, but we just shorten it to voltage because, like I said earlier, just a single voltage really doesn't have any meaning. So if you look at like your household outlets, they're usually around 110 to 120 volts, depending on how far you are from the power plant. But really that's a voltage difference between the two plugs that you'd be plugging into. Thunderclouds, 10 to the 8th. Potential across the nerve membrane is very small. So we deal with voltages like these kind of all the time if you pay much attention to things around you. Alright, let's do a quick example and then call it good. Back to the white pen. Here I've got some parallel plates with a voltage difference of 500 volts, and I've got an electron that's going to fly through that voltage difference from the negative. It's going to fly this way, right, because it's attractive to the positive. And we want to know the change in electric potential energy. So the change in electric potential energy is going to equal Q times the change in voltage, because voltage was delta U over Q. And so we just need to multiply this fundamental charge, which is negative 1.6 times 10 to the negative 19th, multiplied by that voltage of 5,000 volts. And you'll see here that we're going to have a negative change in potential energy, which should always happen when you're speeding up. If you're gaining kinetic energy, you should be losing potential energy. And having this negative on the charge here is important, otherwise this quantity would come out positive. So if we had a positive charge moving this way, it would be gaining potential energy because we would be fighting against the electric field. You need some external force pushing against it to do that, or it had to have some initial velocity, I guess, from something else. Anyway, we do this calculation and we'll get negative 8.0 times 10 to the negative 16th joules, which you might look at and say, well, that is a tiny, tiny bit of energy. Pretty insignificant. But if we do this follow-up calculation and look at how fast the electron goes, it actually goes pretty quickly because this mass is so incredibly small. It doesn't take a lot of energy to have a decent velocity. So here I want to know the speed. Well, what happens to this kinetic, or sorry, this, oh, there, I gave away the answer. What happens to this potential energy that it loses? It becomes kinetic energy, and we don't want it negative anymore because this is a loss in potential energy. It's a gain in kinetic energy. So that's our kinetic energy. We can set that equal to 1/2 mv squared and just solve this guy for v. So v is going to be the square root of 2 times 8 times 10 to the negative 16th times the mass of this guy, 9.1 times 10 to the negative 31st kilograms, and we get a nice quick speed of 4.2 times 10 to the 7th meters per second. So not a lot of energy to go quite quickly.